Hello, and welcome to this video on the scientific process. By the end of this video, you should be able to describe the scientific process, define key terms used to describe the different steps in the process, and recognize how these terms relate to one another. Along the way, we'll include an introduction to concept mapping or concept sketching, and by the end of the video, hopefully, you'll be able to begin to utilize basic concept maps to organize your ideas. As we begin, be sure to have pen and paper handy to ensure full participation and ability to take notes. Also, keep your finger on that mouse or spacebar. When I ask you to pause the video to think something through or to make a prediction, I really mean it. Research shows that students learn better when they're able to think about a question and come up with their own initial responses, even when that initial response is wrong. So if you care about your learning, don't skip this important step. Okay, let's begin. First off, I want you to consider the words that pop into your head when I say scientific process or scientific method. Go ahead, pause the video to brainstorm a list of words that you think relate to the broad subject of scientific process. You can pause the video now. Did you manage to come up with a list? This is mine. That one in the bottom corner says explain. These are just a few of the options, so your list might not match mine, but hopefully there is at least a little bit of overlap. We'll go over some of these terms in more detail a little bit later in the video. And when we do, we'll attempt to draw connections between them and organize our thoughts so that we can figure out what exactly the scientific process is, what it's used for, how it's used, and why it's valuable. Now, as we do this, we're actually going to organize our thoughts and information using a concept map, which is just a way of organizing ideas. How it works is that your big ideas, these are usually nouns of some sort, those are going to go inside circles or ovals or boxes. In this exercise, we'll be using ovals. And then you'll have multiple ovals, all with different ideas, and you'll draw lines between those ovals that represent the relationship between the ideas. And so on the lines, you'll be writing out what the relationship between the two different ideas is. Let's look at an example. Today, we're going to use the concept map to help us learn about the scientific process. Are you ready? We can start by drawing a big circle in the center of our page, and inside that circle we'll write our big idea, which is the scientific process. And then we can get ready to branch out with a lot of important concepts related to our big idea. Now, for this example, I'm actually going to start with a concept map that I designed that's already a little bit filled out, okay? And we're going to work together to try to figure out what goes in all of these blanks and to add a few additional concepts as we go. So let's go ahead and get started. This says that the scientific process can be used to generate knowledge about something, and the scientific process can be used to generate knowledge that can lead to new something. So it's our ideas to fit our goal to figure out what exactly we should be writing in these two boxes. Now there are lots of different options, so let's think about it and see if we can figure it out together. So to start with, what do you think knowledge that is generated via the scientific process is actually about? It turns out that the scientific process helps us to discover things about the natural world. So in that box, it's appropriate to write down the natural world. The scientific process can be used to generate knowledge about the natural world, which is the world that we see around us every day, that we live in, that we hear about in the news. Now, on this other branch, the scientific process can be used to generate knowledge that can lead to new something. Well, there's, again, lots of different options, right? It could lead us to new discoveries, new inventions, new solutions, or new ways of thinking. And any of those would be a great option to write in that oval there. I'm going to go ahead and write new technologies. Okay, so that wasn't so bad. But before I get much further, I think we need to take a step back and officially, formally define some of the terms that we brainstormed earlier. So we're going to start with hypothesis, right? Most people, well, a lot of people at least, when they think about the scientific process or the scientific method, they think about hypothesis. And you might have heard in grade school that a hypothesis is an educated guess. That's not quite good enough for us, okay? We're going to raise the bar a little bit in this class and come up with a bit more formal definition for hypothesis. So, what is a hypothesis? Hypothesis. It's an explanation of how something in the natural world works, right? It explains how something works. Typically, they are based on observations. They must be testable, and that means that they can be supported by evidence or they can be falsified. They can be disproven. Another word that often comes up is observations, right? So what does that mean? These are things that we can see, touch, or feel. In general, observations represent undeniable facts. I saw a cat. It happened. I observed that a cat exists, right? Even though observations are real, they can still lead us to believe things that are not true. So, for example, I was on the UND campus and I saw 20 black cats. And now maybe I believe that all cats on UND's campus are black, right? That might not be true, but it doesn't change the fact that I did observe those 20 black cats, okay? So there's a difference between an observation and an interpretation of that observation, and that's important to keep in mind. The other thing to keep in mind about observation is that it has limits, and a lot of the times these limits are technological or sometimes even social because no one's come up with the new idea to explain those observations yet. One example of observations that led to a scientific theory that was later sort of put to rest in favor of a different theory that was better supported by evidence is geocentrism, okay? So according to geocentrism, the Earth is in the center of the universe and the planets and the sun all rotate about the Earth, okay? This is based on observations, right? If you go out in the day, you can see the sun traverse the sky. If you go out at night, you can actually see the stars traverse the sky in that same direction. So it does make logical sense to assume that all of these things that we see in the sky are rotating around the Earth. However, if we look a little bit deeper, if we take more precise measurements of exactly how the stars are moving, or more to the point, exactly how the planets, the other planets in the night sky are moving, we can find out that it actually doesn't support the idea that the Earth is in the center. And with the addition of more data, more precise evidence, we actually find that the sun is the center of our solar system and that all of the planets rotate in orbit about the sun. So that's just one idea of how observations can lead to hypotheses that turn out to be incorrect, okay? So that's okay because science is something that is a living body of knowledge. It changes and evolves as people change and evolve and as our technologies change and evolve. This doesn't mean that observations are invalidated. It just means that sometimes when we have a more complete data set, we're led to different conclusions. Okay, so talking about observations and data means we really need to talk about experiments and structured observations, okay? So experiments and structured observations are designed to gather evidence to support or refute a hypothesis. Note that I did not say to prove a hypothesis correct. The scientific process actually doesn't provide a mechanism for us to prove anything, because you never know what new advances in technology and new experiments are going to teach us about the natural world. Okay, so we can support a hypothesis, and if it has a lot of support from a lot of different experiments, different kinds of experiments, then we can even begin to call it something that we term a theory, which in science is about as close to truth as you can get, but sometimes even theories are incorrect because in the scientific process, it's a mechanism for proving ideas wrong. Okay, so we can disprove things, or we can provide support if it seems to be a good explanation, if it seems to be an accurate description of how something in the natural world actually works. So when most people think of the scientific process, they often think of laboratory tests, right? You have your dependent and independent variables, and you set up an experiment and you measure things, and that's true, that's all part of the scientific process, but it's not the only way to gather data. Especially in earth science, we often design surveys that go out and in a very structured way examine the world. So for an example, we have surveys that have measured topography, right? We know the height of various locations on the planet. That's an example of a survey. Another survey might measure the temperature all over the globe. Okay, so that's a scientific data set that's collected by systematic measurements that are not taken in a lab but are taken out in the world. A final way of collecting data that's quite common is to actually go to the library and pull together a lot of different sources of work from people that have come before you. And when you do that, sometimes you can actually generate a new data set. So one example of that might be looking at old records from ships to figure out what cargo was carried in the 1800s, and you can build up a data set of what all that cargo was and how it changed over time. Okay, so that's an example more in line with library research than a laboratory test or a survey. So I keep mentioning data. As I said in the last slide, data can be generated from experiments. It can be generated from structured observations. These are our surveys. It can also be generated from more library style work. In general, data represents undeniable truths, okay? These are observations that have been made about the world. They might include the laboratory tests, the survey results, or the outcomes of library research. Now, once you have that data set, it's up to a scientist to analyze it, okay? So the analysis part is work done in order to make sense of the data set. So this might include making graphs of the data, applying statistical relationships, using computational models to calculate something. All of these are sort of ways that we have to manipulate data into ways that make better sense to the human brain, right? Because if you're just staring at a bunch of numbers, then you might not know what they mean or how they relate to one another. But if you use a computer to compare different data sets to each other, or for example, you could plot the time of day and the temperature, then you might be able to say something about what happens to temperature over the course of a day, okay? So the analysis is the methodology that we use to make sense of the data. Which brings us to interpretation, okay? Interpretation is when we take that analysis and we try to figure out what it is that that data is telling us about how the world works, okay? So interpretations enable us to make conclusions based on evidence that either support or refute a hypothesis, okay? Now, interpretations are not undeniable truths, right? They are how the human brain is interpreting the information in front of them. And there are often multiple different interpretations, even for one data set, okay? If future technology advances, then new evidence might be provided and interpretations might need to be drastically changed in light of this additional evidence, okay? So it's important to keep that in mind. Data in general represents facts, and interpretations, that's where scientific judgment comes into play, and interpretations are likely to change over time or with better data collection processes versus the underlying data itself that shouldn't change unless it's some sort of data set that changes over time. For example, the temperature outside over the course of a day. Now, another really important part of the scientific process that a lot of people forget about is knowledge sharing, okay? If you go out and do an amazing scientific study and come up with some amazing interpretations and just amazing new ways of viewing the world, but you don't tell anyone, you're not really contributing to the scientific process as we know it today. So what is knowledge sharing? Well, it's referring to the sharing of the results of experiments, right? This includes the experimental design, the analysis, and the interpretation. You have to share all of those things so that other people can make a sound judgment on whether or not they agree with your interpretations. Now, who do we share this information with? Lots of people. Usually it's first sent out to other scientists. And the word that we have for this, the way that we typically do this, is a process of peer review. Peer review means that you're sending your work out to your scientific peers, people who are experts in whatever it is that you have studied, to get their opinions on what you've done. And sometimes they'll suggest ways to make it better, or they might disagree with you, and that will force you to think a little bit deeper, maybe change something, or maybe you stand firm and you say, no, I think that you're wrong because of this reason. And so it's in this peer review process that scientists, the experts in a field, really have a deep discourse about the interpretations of a study. Sometimes these conversations will also include experimental design. If you set up your experiment in such a way that the data isn't really valid, hopefully another scientist will be able to point that out to you. Now, of course, the other really important aspect of knowledge sharing is to share with the general public, okay? And that is often done through popular media and news articles, and sometimes you might even include sharing scientific knowledge in the school system, because most systems around the world think it's very valuable to teach students about science and about the theories that have been built up over the course of human history that begin to explain how the natural world works. This brings us to the idea of a scientific theory. Okay, so sometimes people get confused about scientific theories because we use this word theory a little differently than people use in everyday language. In science, a theory is an explanation of some aspect of the natural world that has been repeatedly tested and verified in accordance with the scientific process. This means that you have not just repeated the same study over and over, but you've come up with different experiments, different ways of testing the idea, and it really seems to be supported by a very large variety of evidence, lots of different types of evidence. Now, it's also sort of common that we reserve the word for explanations that explain a large variety of observations, okay? So for example, the theory of gravity explains why the planets orbit the sun, why my phone falls if I drop it on the ground, why the Earth is denser at its center, and many other observations that we can make. A law, on the other hand, is a description of an observed phenomenon, okay? So laws do not explain why the phenomenon exists or what causes it. They just describe what happens. Often a law can be described by mathematical equations. Now, sometimes things have both a theory and a law. So the theory of gravity explains why objects fall together, why objects fall towards the center of the earth, for example. And the law of gravity is a mathematical equation that describes how those objects fall towards the center of the earth. So a theory is an explanation of how something works, and a law is a description of something that happens. Okay, this brings us back to our scientific process concept map. In a second, I'm going to ask you to go ahead and begin to fill out the rest of this concept map, keeping in mind that it's really a judgment call. There are many, many correct answers to how you can go about filling in these blanks and adding additional ideas to the map. Just as one example, I'm filling in sharing results, okay? So the scientific process includes sharing results. And then hopefully you can think of at least 2 sub-branches that you could add to that. So the scientific process includes sharing results, for example, something, and for example, something. Or the scientific process includes sharing results with someone, and fill it out that way. Okay, now it's your turn. Hopefully you have managed to sketch that example concept map into your notes. It's going to be your job to fill in the empty circles with ideas that make sense in the context of this concept map. Remember, some of those relationships have already been filled in for you, so you need to find the concept that best fits within that circle to make those relationship lines make sense. After this, you're going to add sub-branches to expand on these ideas, okay? So you're going to include examples of who knowledge is shared with when you share it out to the world, okay? So you're going to add additional ovals and additional lines to the map in this part of the process. When you draw those lines, make sure you write down the relationship between the 2 concepts on the line that connects them. Finally, don't write down an idea more than once, okay? If you find yourself wanting to write down an idea in multiple places, instead, just draw an arrow to where that concept already exists in the map, and be sure to write the relationship between the 2 concepts on the line that you've drawn. There's more than one right answer here. Don't be afraid to give it a shot.